All right, so we're going to get into chapter 18, which is on hypothesis testing. And so this is a very useful chapter, very practical. And I think a good way to get started is with an example. So first example, after a new engineering process, the cracking rate of 400 casts fell to 17%. So um, company is making whatever these casts are, and so the cracking rate, they took a sample of 400, the cracking rate fell to 17%. Um, and using the old process, the cracking rate was 20%. So this new process perhaps seems to have caused fewer of these to be cracking. So the question is this new process, or is the drop in the cracking rate due to the new engineering, or is this just random chance? So obviously we've talked about with sampling distributions, you can take a sample and your sample proportion or the sample mean, as the case may be, should be close to the population proportion or the population mean. But it's never going to be, well, rarely, if ever, it's rarely going to be exactly what the population mean is or the population proportion. So there's always going to be variation. So how much variation would be due to random chance versus how much is because of something else, in this case, the new engineering process. So we're going to start with what's called the null hypothesis. And the null hypothesis is just some parameter. And in this case, we're going to be looking at a population proportion, but some parameter equals whatever hypothesized value is. And you can take this to be historically what it has been, or what you expect it to be, or what you hope it is. But it's always, the important part is some parameter, population number, and equals. The equals is always on the null hypothesis. And in this case, historically, the cracking rate has been 20%. So we're going to say P is 0.20. So that's our population proportion equals historically what it has been, in that case, 20%. Then we have an alternative hypothesis. The alternative is that it's not equal to this. So it has changed in some way. So parameter is not equal to the hypothesized value. And it doesn't have to be, so in other words, it could be less than, it could be greater than, or we could be looking at both sides of that. Maybe it's, you know, interested in either way. We'll talk about that. In this case, we're looking at a drop. So the alternative hypothesis would be P is less than 20%. And so we're going to see how likely would it be that we'd get 17% or less. So just kind of asking the question, what if the cracking rate had been 1%? So fell to 17%, but what if it fall all the way to 1%? That would clearly indicate a change from 20%, because you're not going to get random variation that goes all the way down to 1%. But if it had been 19.8%, we would probably be skeptical, because that is going to happen. If your population proportion is 20%, you're going to be around that. You know, there would be some variation, but 19.8% is obviously not that far away, and so that would not be unusual at all. So let's work this problem. And if you did what we talked about in chapter 16, this is very, very similar. And in fact, we're really just kind of formalizing what we were doing then. So the steps are going to be the same. And so first we need to check the conditions. N is going to be 400, P is going to be 0.20, and then of course we could add Q in there. 1 minus P would be 0.8. Independence, so we will assume independence. We will assume the 10% condition is met because the sample is 400. Probably the population of all these that they have ever made is more than 4,000. So the 10% condition would be met. We can easily check the success failure condition. So 400 times 0.2, that gives us 40, which is more than 10. And then n times q would be 40 times 0.8, and that would be 300 and, I'm sorry, that would be 80, not 40, but greater than 10. And then n times q would be 320, which is also greater than 10. So all of these are met, conditions are met. And so then the next step would be to find standard deviation. And this, of course, is a categorical variable, so these things are either correct or they're not. And so the standard deviation of p hat is the square root of p times q over n. And so we have the square root of 0.2 times 0.8 over n is 400, and square root, of course, is over the whole thing. And we get 0.02. So we have a mean, if you will, we have a standard deviation, and now we can look at the normal model and figure out what this probability is. So let's find our z-score here. And so the z is the data point, which would be the 0.17 minus the 0.20, and over our standard deviation of 0.02, and that gives us a z of negative 1.5. And so then we can draw the curve. We can put 0 in the middle. We can put our z-score over here. And in these hypothesis test problems, examples, we are always going to be shading away from the center because we are always talking about, we're considering how unusual this sample is. So we're considering hypothesis testing, we're considering how unusual something is. We can find the z-score if you like, and then we're going to be going away from the center. So these will always be shading away from the center. Other problems, it can go either way. It depends on what the problem is asking, but in these types of problems, we are always shading away from the center. And then we can find the probability using the normal CDF on our graphing calculator. So lower bound, just pick negative 10 or negative 100 or negative 1,000. Upper bound would be negative 1.5, and then 0, and then 1 for working with the standard model. Or, I mean, you can also do this without finding the z-score, in which case we'd have the 0.2 in the middle. We'd have 0.17 over here and still shade that way. In this case, our lower bound would be 0, and our upper bound would be 0.17. Our mean would be 0.20. Our standard deviation is 0.02. So either one of these, they give the same answer. So 0.067. And so what that means is there is a 0.067% chance of getting a sample with a cracking rate of 17% or less if the actual rate is 20%. And so we'll talk more about what that probability means on the next video, but hopefully you can see we're kind of setting these up in the same way. You can use a z-score or not, if whichever way you prefer. But they give you the same thing. But that's kind of the idea to get us started. We'll talk more about what this probability means in the next video.